Well, g'day and welcome aboard everybody to the latest online event from Markham. Easy, sustainable and safe around protection for concrete infrastructure in the mining and related industries. I'll just get this share going again. Alrighty, so with us today we've got Doug Hamlin, who's going to give you the pucker on all things in relation to the durability and structures. There is a questions button down at the bottom right hand side of your screen and a chat button. We'd be very grateful if you want to put any questions in there that you may have as we go along, and we'll have a live answer session towards the end. Doug, without further ado, would you like to give us a bit of an introduction about yourself, and then we can take it away?
Yeah, thanks, Brendan. Yeah, my name's Doug Hamlin. I've worked with Markham for just over 14 years, so a lot of experience through the project management space, application, right up what I do today with the advice on projects, specifications, and advising on how to extend service life of concrete structures. So yeah, keen to discuss this topic today.
Very good. So do you want to give us the learning outcomes and take it a step forward from that point?
Brilliant. Yeah, so today we want to have a look at the obviously the challenges that the mining environment in particular faces, how to choose the best admixture but best strategy for the long-term service life here, and then talk around the sustainability side of things, safety and ease of use, these things that come into play when you're looking at service life and durability options. I would note too that this is focused on mining, but it's relevant to other areas in the marine and civil space. Mining does have a very harsh acidic and chemical attack, which is, if it can survive in a mining environment, it's a good chance it's going to survive in a marine or civil water infrastructure, that type of thing. So yeah, if we go on to the next one there. So yeah, firstly wanted to look at the mechanisms that attack concrete. So what are the main challenges? In the mining, we're seeing a lot of chemical and acid attack. This also includes the hypersaline water. We're seeing mine sites with the water from the dewatering, the groundwater coming in at around, or it's anywhere from about 3 times to up to 8 times on the worst case, the salinity or the saltiness of seawater. So you're very aggressive into that environment. You've also got in the processing areas the acid, the ammonium sulfates and everything that are used in part of the processing and part of the mine, processes there. The extreme weather, often these mines are in remote locations. You've got high temperatures, and then sometimes it's tropical too. So you get the concrete absolutely saturated, and then it goes dry, and you get that sort of cycling happen. The steel corrosion. So obviously this is a result of the chemical attack, a result of the contaminants getting into the concrete, causing that rebar to rust and expand and pop the concrete off. This is obviously driven by moisture into the concrete. ASR and DEF, they are 2 different topics, but they work on a similar mechanism whereby the internal matrix of the concrete expands and causes cracking, which speeds up the ingress of contaminants. Carbonation, soft water attack, not so much in mining, but yeah, it is essentially a light acid attacking the surface. You've also got, with the mine sites, you've got a lot of heavy machinery moving around, so you've got that load and abrasion there. Some of the materials used or that they're mining out, lithium, for example, is very abrasive onto concrete. And then lastly, the material supply. So getting a lot of these are trucked from, say, a centre like Perth into, it could be 1-2 days into the site, so they want to limit down how much material is going to site, and getting something that's working in that space, also on site, not taking up too much room, and is easy to dose and use inside the concrete. It's not causing any detrimental effects to the placing and the set times, that sort of thing. So yeah, a lot of things to think about in this space. It's probably one of the harsher places to pour concrete, but yeah, there is things we can do to overcome it, which we'll go on to shortly. Go to the next slide there. So yeah, thinking about these threats and then the impact of them. So downtime is probably the biggest one. Mine sites are there to make money essentially out of the ore that they pull out of the ground. If you have any downtime, that's costing them, and they do everything they can to limit it. Concrete repair, unfortunately, is one that does pop its head up, where you get that breakout, repairs are done, and then because you're not, if nothing's done to protect that repair and protect the concrete around it, you get more breakout beside that repair, and it kind of cycles on like that, and you get that happening sometimes as soon as every 2 years, but normally around that 5 to 10 year time period. And then ultimately, if you're not, these threats can cause the structural integrity or the lifespan of that concrete to be reduced. So it's not doing the job it was intended to. It's not providing that foundation or that structure for the processing plant or for the mine site there. Other things is traditional mix designs. So when you're looking at some of the things like microsilica is a good example. There's other admixtures that can interfere with the critical properties of concrete. So things like the slumps, the set times, strengths, those sort of things need to all be taken into consideration when you're choosing a durability method to overcome these threats. You don't want to be getting high durability, but then having a concrete that's very difficult to place, for example. Go on to the next one there. So yeah, Markham recommends protecting the concrete from day one. That's the most, or the best way to be sure that the concrete is going to get the best chance. So you're not letting any contaminants in to the concrete from day one. You're not letting that concrete be attacked. You're getting that protection right from the very start. So we recommend the use of hydrogels. They do a very good job of durability, but then they also fit into the construction program or the construction methodologies very well too. So what they do is it's a colloidal silica that reacts with the calcium hydroxides in the concrete, or the alkalis that are always as a byproduct of the cement reaction, and they form a hydrogel within the porosity, and it stops the moisture moving through the concrete. Now, as soon as you stop moisture, you stop that or block that contamination from being able to move through the concrete. So if that was from day one, you're stopping it. If you do have a structure that's down the track, there is options to spray apply and halt or arrest that deterioration at that point. But the key is that it's stopping that moisture and reducing that permeability of the concrete, which in turn results in long-term durability. Next one there, Brendan. So yeah, on constructability, I touched on it before, but with anything we're doing with concrete construction, the key really is the constructability, or how easy it is to place the concrete, how easy it is to achieve the structure needs, that type of thing. So we believe that quality starts there. So it starts with being able to place the concrete easily, to be able to dose an admixture into the concrete, to be able to pump it, whether you're doing shotcrete, anything like that. It needs to be able to fit into all those methodologies and not have any detrimental impacts or interrupt that process too much. So with hydrogels, because they are a liquid admixture, they go into the mixed water, and they don't impact your strength or don't impact your pumping ability or the workability of the concrete. In fact, they actually make it better because you are essentially lubricating the mix and you're using up more of the cement in the hydration process, so you get a more workable mix. They are compliant to the 1478 type SN standard, so that's that looks at all your critical things like strength, slump, shrinkage, bleed, all those things, and we comply there. So there's basically, if you take your standard concrete mix and you're wanting to make it more durable, you just take that mix, add the hydrogel to it, and then carry on. There's no need to revisit all the mix designs, everything there. Next slide, Brendan. So yeah, sustainability and safety. This is a strong commitment here at Markham. In terms of the hydrogels themselves, they are a very low carbon emitting product as far as the manufacture and freight, everything that's associated there. The Conquer range that we deal with actually comes from as byproduct of geothermal power stations in New Zealand. So it contributes very positively there. The product itself is water based. It's a non-crystalline, so it doesn't have any silica sands in it. Crystalline silica in it, so it's not posing a silicosis risk. They don't smell, so they don't give off any solventy or ammonia odors there, and they have a nil VOC content, so no solvents, no volatile organic compounds. So as far as being safe, it's excellent there in terms of handling, transport, dosing, placing, everything that you need to do with the product or with the concrete essentially on site. We do have the EPD declarations available there, and they can be put into your project numbers if you're going for a Green Star type build, and they're published, available on the EPD website there. So move on, please. Back to the topic of being easy to use. So I mentioned earlier they are liquid, so a water-based liquid. They have a reasonably small amount of active ingredient with the colloidal silica, but because the colloidal silica is a nano-style product or nano-scale product, the size particles we're dealing with are very small compared to, say, something like a microsilica or fly ash or something like that, where you've got bigger particles. And what that means is that you get more reaction with the less amount of product. So with typically into concrete mixes, we're putting between 2 and 3 litres of product per cubic metre. Now this is a lot lower than some of the powdered admixtures you're putting in, and then also a lot lower than some of the other traditional admixtures, which are upwards of 20 litres per cubic metre. So it is very easy to put in. It doesn't affect your water demand or anything like that. And, as far as transporting them to site, logistics, that sort of thing, it's a very low cost there. What's more important, though, is that once you put that admixture into the water, into the mixed water, and it goes into the concrete, that mix is very easy to pump and place. So we're getting regular feedback of pump pressures being able to be lower, so less wear and tear on the machines, that type of thing. And then that translates into being easier to rake and screed for the granos on site as well. So if we could go to the next one there. Just want to have a look at a couple of projects here. So first up, the Mount Ida project. It's a lithium and gold. Lithium is a very abrasive material, so it when that, moving it around on the slabs, that type of thing, you get that wear. It's harsh on the concrete. Also on this site, being remote, had the hypersaline waters as well. So in the process plants, that type of thing, the wash down was all extremely high salt content. So they used the hydrogel admixtures there to protect against that. As another or a side benefit, as you might say, it was poured in some very hot conditions between 35, 40 degrees. And because the hydrogel is essentially hydrating the concrete and it's holding that moisture in the hydrogel, it stops it escaping out of the concrete and reduces that cracking, reduces the shrinkage of the concrete down. So, not saying we don't get any cracking. Would be stupid to say that, but we'd get a lot less than you would with a standard concrete there, and that translates into longer service life because you're not having those cracks transport contaminants into the concrete and start that corrosion process. Next one there, please. The next one is the Murrin Murrin project. So this is really a flagship project for us in the mining space. To paint a bit of a picture, the previous methodology they were using was lasting around 18 months to 2 years before you'd have major damage, and it would need to be replaced. So there's a wide range of attacks on this project, from sulfuric acid, ammonium sulfate, that type of thing. And essentially what it does is it gets into the concrete and the acid obviously breaks it down. The ammonium sulfate gets in and pulls the calcium or the alkalis out of the concrete. Either way, you get the concrete breaking down and you get like these 40 to 50 mil gouges through the concrete. And then you'll get, say, 150 mil diameter pits forming in the concrete. And once they start to form, you're losing your integrity of your slab and you need to repair or rip out and replace that concrete. So they moved across to using a hydrogel as an admixture into the concrete. So the liquid, and then they also spray applied to give a decent cure, but then also to provide extra protection to that top surface. They spray applied a hydrogel as well, and then from there they were able to carry on. They always do an epoxy coating on any of the concrete in the process plants. What was interesting though is that because with the previous system, as soon as you got a pinhole or a crack in that coating, it would go straight through and start gouging out the concrete below. When the hydrogels were used, you might get a crack or something, but it's only attacking that very, very top surface. It's not going down into the matrix of the concrete, and you don't get that gouging, or you don't get those big pits forming. Now, this is to two reasons. One is the moisture can't, the acid can't penetrate physically into the concrete. It's limited to that top surface. But secondly, because the hydrogel is consuming the calcium hydroxide at that first, at that pour stage, it means it's not available for the acid or for the ammonium sulfates, the chemicals in that, to attack and leach out of the concrete. So yeah, excellent result there. The Carapateena project is a great example of the hypersaline water. So this concrete here, they're getting around not even 5 years before there's needing major repairs to the plinths and the buns in the processing plant. This is a very high concentration of saline in the water here. So yeah, this is both underground and above ground. And what they're proving is obviously the durability effects of the hydrogel and standing up to the hypersaline water, but they're also getting a better result off the form. So as I mentioned earlier, they make the concrete more workable, easy to use. So you're not getting as much honeycombing and that sort of thing in the concrete. You're getting better compaction, better quality concrete. It's easier to move around in place, so the guys can put a bit more time into the finishing it, that type of thing. So essentially it's de-risking the concrete pour there. Obviously, again, harsh environment, the middle of nowhere, and very hot temperatures for most of the year, and then they'll get, thunderstorms and the concrete's absolutely saturated. It gets washed down pretty much every day with the groundwater. So yeah, it faces some fairly heavy challenges there, but it is standing up well, and it's something we're going to keep an eye on into the years to come. And yeah, it's a good example there. So yeah, it's sorry, Brendan.
No, I was just going to say, yeah, we'd be very glad for the audience to contribute. Sorry, please do go on.
No, that was all. I was just going to say the same thing. So.
Anyway, the chat always asks you to say something nice, and somebody has said something nice, so appreciate that too. Thank you very much. Just while the questions are coming in, just question to my mind, which always comes up. Can you say something about the permanence of the treatment, Doug? It doesn't need to be reapplied frequently like a topical coating might be.
Yeah, sure thing. Yeah, so the hydrogels, once they form inside the concrete, so whether this is as an admixture or spray applied onto the concrete, they react with the alkalis with the calcium hydroxides and form a calcium silicate hydrate hydrogel, which is essentially the same as the binder or the cement paste that you get in concrete. So once that reaction's taken place, it's very hard to reverse that, or impossible to reverse that reaction. So essentially that hydrogel is in there for the life of that structure. So it can't be removed or abraded off the surface, so to speak, or it doesn't wear like a coating does. So yeah, essentially they are permanent. What you do need to think about is the wear and tear on the structure, loading, that type of thing, and the actual design life of the structure itself is more what comes into play there.
Very good. We've got a question coming as to what is the process to get this approved by structural engineers?
Yeah, that's a good question. So typically we go through a process of they'll want to see things like the strengths, the set times, all those critical properties that they're not going to have any impact on the structural design side of things, which we supply that. Secondly, it would be things around the actual durability performance. So looking at what that cover concrete, what improvements we're getting there. So things like water penetration into the concrete, so under high pressure, chloride diffusion through the concrete matrix, so where they accelerate chloride ingress into a structure and see the resistance there. And then things like carbonation, acid attesting, that type of thing, really depends on what the project is trying to achieve as to what they want to see. But yeah, it's essentially those two things to make sure it's not going to impact the structure and that it is going to improve the durability. So yeah, and once we show those two things, the approval goes from there. You're muted.
Well, that's fair enough. Thank you. And another one here in the chat. Hydrogel samples in demo bottles that are over 5 years old. And the hydrogel's in original condition. Thank you, Locke. I appreciate that feedback. In micro pores would be easy to control and longevity pretty well unlimited. Did you want to comment on the comment, Doug?
Yeah, that's good, and I 100% agree. The hydrogel demo that we do is a fairly accelerated, and it makes a lot of gel in a sample bottle. But when you're talking about concrete microstructure, you're talking microns and nanometers size. and that gel is formed in those pores and porosities. And yeah, agree. It would it's a lot harder to remove or from those micropores, and yeah, pretty much impossible or unlimited, as you say. Agree.
I'm just wondering, perhaps if you'd like to say something, Doug, about where, if somebody's involved with marine structures or perhaps a local council, what sort of situations they might see the extreme environments needing special protection, such as similar to what we've been talking about in the mining space.
Yeah, sure thing. So firstly, in the council space, it's around water retaining structures. So the hydrogels, the way they work is they waterproof the concrete. So in water retaining, you by waterproofing the concrete, you're stopping that moisture getting to the reinforcing steel. A lot of the times you've got chlorine used to in the potable water. It might be, if it's in a wastewater environment, you've got hydrogen sulfide attack, that type of thing. But if you can stop that moisture from penetrating into the concrete, again, you limit the attack to that very top surface and essentially slow it down. In the marine space, we do a lot of projects on the coastal side of things, so in wharves and pontoons, jetties, that type of thing, where it's about protecting against that wet and dry or tidal zone, where you get the corrosion happening because it's essentially every time the tide comes up, it loads the concrete up with salty water or with chloride, and that generally increases over time, and you get that corrosion process, you get the spalling and the breakout of the concrete. So that can be used to prevent that from happening, prevent that ingress from happening. But also, if you are repairing a structure, to protect those repairs and stop that cycling effect happening. So if you think about when you do a repair, the concrete around the repair is still coming up to as worse condition as the repaired area. And if you're not doing anything to stop that carrying on that process, it's going to keep cycling. So being able to stop that moisture moving in that area, or in that between that repair and the parent concrete, stops that corrosion process from progressing. So yeah, that's a couple. There's obviously many project scenarios, and that's what we encourage as a company to talk to us about your particular project. It's there's some cases we will want to be a part of a overall solution with other products and other repair methodologies, that sort of thing. And then there's sometimes where, if it's more as a prevention, we can just use a hydrogel, and you're protecting the structure from that side of thing. Obviously, from day one, using the admixture in the concrete is all you're needing to do there. So yeah, that's hope that's helpful.
Yeah, that's good. Just a further comment from Locke on the chat in regard to corrosion, mentioning that the hydrogel doesn't actually remove the moisture from the concrete, but does stop the wet-dry cycle.
Correct, yeah.
No oxygen getting in, particularly below seawater, stopping the oxygen, which is the key to what hydrogel does.
Correct, yeah. Yeah, that's an important point. So we're not removing the moisture from the concrete. So we're holding it in there in the form of a hydrogel. What we're doing is creating a state where that moisture is not harmful to the structure, so it can't move around and it can't contribute to that corrosion process. Another way to look at it is, if you think about the corrosion of reinforcing steel like an equation, so you need moisture, oxygen, and some form of aggressor, so a chloride or an acid or something like that. If you're taking away that moisture out of the equation and reducing the oxygen to the corrosion process, you're taking away the two factors, or the two necessary factors for that corrosion to happen.
Yeah, no, that's good. If everybody's okay with that, we might just walk to the summary. And do you want to just touch on the points again, Doug, just so they're fresh in everybody's mind?
Yeah, sure thing. So in in summary here, the hydrogel admixtures are a great use in the mining environment to extend the service life of structures. So the safety side of things, they are safe for both storing and dosing, and then also on site when you're placing and pumping, that type of thing. They, in terms of sustainability, they extend the service life of concrete structures, and getting the most out of your structure from day one. You're doing the best you can by stopping that moisture getting into the concrete, stopping those contaminants getting in from the very start. And then the maintenance side of things, so those repair cycles we talked about, you push them out so you're not having that happen as regularly as they were happening. So you're reducing that downtime, reducing the costs associated there and the interruptions to the structure or to the operation that the structure's in. So yeah, thank you very much for attending today's webinar. I appreciated the questions and your attendance. And if you do have any further questions or projects you'd like to discuss, you can reach out to us on the website, or there'll be a follow-up email to this event. You can reach out and we're happy to discuss.
Yeah, thank you very much, everybody. Appreciate the inputs that came in. It was good. And as Doug says, we'll share the contact details on a follow-up email and be glad of your feedback. Thanks, everybody, and have a great day.